think we all think that Colin did very well punting while the sort of technical things were being solved. So well done on doing that, Colin. Okay, so our next talk is by Anastasia, and we're moving on from fault localization to reasoning about round-off errors, but also round-off errors in the large, which is a very tricky problem. So it sounds like a very intriguing talk. So when you're ready, Anastasia, take it away. This is joint work with Eva, who's also in the audience.
Okay, thank you for the introduction. So today I'm going to tell you how to scale up rounding error analysis for loops over data structures. Now, when we implement real-valued algorithms in finite precision, we inevitably introduce rounding errors, and especially for safety-critical software, we want to make sure that these errors are bounded and compute a sound worst-case upper bound for these errors. For instance, we can compute an absolute error bound that would quantify the difference between what finite precision computation computes for us and what is the ideal expected result of this computation across the input domain. For instance, for such a straight line code, we can use one of the state-of-the-art tools to compute the absolute error bound and the real valued range of the value of the resulting value in a matter of seconds. So for small straight line code, there are plenty of tools that can compute tight error bounds for both linear and nonlinear arithmetic. However, scalability of such methods is still work in progress. And among other things, loops are presenting a different challenge that is probably best illustrated with an example. Say you have a loop that sums up 100 elements in the range between 0 and 100. And to the right, we depict the dynamically sampled rounding error for this loop across different iterations. So as you can see, the error varies a lot across different iterations. And generally, there is no obvious correlation among the number of iterations and the magnitude of the error. So what we can do with that, we can try to reduce the analysis of loops to analysis of straight line code. And for bounded loops, in particular, if we can statically deduce the number of iterations, we can perform unrolling, which works well for small loops. But again, if you have large loops, then such an approach does not scale. An alternative would be to find an abstraction of a loop. Again, finding an effective abstraction is actually challenging because standard static analysis approaches, such as applying a widening operator, does not work well for rounding error analysis because it often returns trivial error bounds. And other methods that actually do deliver more precise error bounds require additional input from users. For instance, finite precision inductive invariant, which by itself is already challenging to compute. So a key idea of our approach is to use a functional way of specifying our loops. And in particular, we focus on loops over data structures, such as vectors and matrices. And the benefit of specifying the algorithms in functional way is twofold. First, we allow a user a concise way of specifying the algorithm, and also we can benefit the analysis because, say, if we are given a map over some vector, already at syntactic level, we know that there is no data propagating across different iterations of this map. And in order to use this information, we also defined an abstraction over data structures that ideally will allow us to avoid duplicate computations in the analysis and scale up. So now let's have a look at the example. Say you want to compute a heat distribution over some one-dimensional line, and you are given a set of points with initial values for the temperature. And say you want to compute the temperature after n time units in the middle of this line. So what you have to account for is that neighboring points affect the temperature of each point. So you have to compute it for each point at each time unit repeatedly until you reach this desired number of time units and your central point. How do you implement such an algorithm? So you can use an imperative style loop, which works fine, but you have to use two nested loops with rather non-trivial loop exit conditions, so maybe error prone. And moreover, if you want to use state-of-the-art tools that can actually analyze, report rounding error bounds, more likely you would also have to unroll this loop and obtain over 1,000 lines of code. So what we propose to do instead is to write it in a functional style. And then you end up with just 6 lines of code, and there are no explicit indices in this algorithm, so it is potentially less error prone. And let me jump a little bit ahead. If we analyze such a program in a functional style, we are reporting error bounds of roughly the same magnitude of errors compared to imperative and unrolled loops, but we can do that much faster. So let's rewind and let me tell you how we actually got there. So we determined that in order to implement this analysis, we need 3 major components. First, the functional domain-specific language that operates over data structures, then an abstraction of these data structures, and transfer functions that actually operate on these abstractions. Let's start with the first one. So following previous work, we determined that our DSL should have real-valued semantics. First, it provides a clear reference semantics for arithmetic operations, and it is also more intuitive for users to write in real-valued. In such a way, we can just provide a finite precision as a parameter to the analyzer and analyze rounding error for a particular precision. Now, if we want to analyze loops that traverse a data structure, we need to know their size. And in our domain-specific language, we propose to specify the maximum size of a data structure because results of the smaller size data structures will be subsumed by our analysis results. And last but not least, as for any rounding error analysis, you need to know ranges of values. For instance, we can specify that all elements in our input vector AX are in the range between 1 and 2, or we can also be more precise and say that there is a subset of elements that has a different range. In this particular example, it's a smaller range, but can actually be anything. Now, what is left to do is to determine operations that actually implement the algorithm. And here, it's just to give you an idea of the size of our DSL. So the design of the language itself was guided by practical applications that we found in open source projects of different domains. And we can roughly split it into 4 different groups of operations. So our DSL supports standard higher order functions, such as map, fold, and filter. And also there are variations with an explicit loop counter. Element-wise arithmetic operations that perform operations on the elements with the same index of the input data structures. Domain-specific functions, for instance, matrix multiplication that is needed to implement neural networks, and also non-numerical operations such as appending an element or adding a padding around a matrix or a vector. For instance, using our domain-specific language, one can implement a layer of a neural network like this, where we multiply a matrix of weights with an input vector, then we add a vector of bias, and then we implement the rectifier linear unit using a functional map and a maximum over an element of a data structure and 0. So the next component that we need for our analysis is an abstraction of data structures. Again, let's go back to our simpler example with the map. Say you know that there is no propagation of values happening across the iterations, but if you don't have any useful information about the input vector itself, then what you're left with is state-of-the-art, just unroll and compute for every element separately. Now what we propose to do instead is to group the elements by ranges. For instance, if we know that all of the green elements are in the range between 0 and 1, and all of the orange elements are between 2.5 and 4, and we know that there is no propagation of values across iterations, it is sufficient to compute once per group of each color. So we've introduced our data structure abstraction to group elements by range, where each group is represented using a set of indices. So here n stands for a dimension. It would be 1 for vectors, and it would be a tuple of indices for matrices. So indices inside one set do not need to be consecutive, but they have to be unique and valid indices of a data structure elements. So in different sets inside one abstraction must be disjoint, and a union of all sets should cover all possible elements of this data structure. Since our analysis tracks values of variables and also errors on them, the abstraction also accounts for tuples of the ranges. And we can get these abstractions either from input specification for input data structures or from some transfer functions that generate fresh data structures inside our algorithm. Again, let's return to our example with the heat. And here from the input specification, we see that the input vector has the size 33. So valid indices will be in the range between 0 and 32. We also know that the elements with indices from 1 to 4 have this special small range, and all other elements will be in a different group with a range from 1 to 2. Inside our algorithm, we are also introducing a new vector. And notice that the first and the last elements of this vector have the same range. Well, actually, it's a constant, but it's a point range. And the middle element will be put in a separate group with the only index 1. We also have the same abstraction for errors. I'm just not showing it on the slide to make it a little bit more concise. Okay, so now that we have our functional DSL and the data structures, we can combine them together and actually design the analysis. The general idea is to analyze as rarely as possible, so potentially analyze only once per each unique range of inputs. In a way, you can say that we are reducing the analysis of loops to analysis of straight line code, and unlike the typical unrolling, we are only doing it once per group, so you can say it's a piece-by-piece unrolling. And once we unrolled, and also for scalar operations that appear in the algorithm, we apply existing baseline data flow analysis as it is implemented in tools like DAISY and Fluctua. So in this work, we focus on IEEE floating points, but our approach is directly applicable to other finite precisions as well. Now, depending on the exact semantics of each operation, different operations will benefit differently from our approach. Let me walk you through that. The simplest case is non-numerical operations, because they by themselves do not commit any error, but they do affect an abstraction. For instance, if we want to add a padding around some matrix A, for which all elements were in the same range, we need to shift the indices in the column and in the row by 1, and also add an additional group of elements that accounts for the first and the last row in a column with the range 0. Operations that benefit the most from this once per range analysis are arithmetic operations, in particular unary operations can be, because there is only one input, we can apply directly only once per range evaluation. And that it would work for unary minus, square root, transcendental functions, and also a map, because it's also a unary function, just a user-defined. A special case of a unary function that also benefits from this once per range evaluation is a filter. Because it contains conditionals inside the definition, we want to avoid creating additional rounding errors, and we restrict the analysis only to predicates of a simple form where we compare a variable to a constant. Another thing that makes filter so special is that it's the only operator for which concrete semantics are not exactly mirrored in abstract world. In the concrete world, a filter would create two disjoint sets, one that satisfies a predicate and one that doesn't, and only take the set of elements that satisfies the predicate. But in the abstract semantics, those sets are not necessarily disjoint, so we have to account for that. And in order to stay sound, we over-approximate the resulting data structure and take all groups of elements that may potentially satisfy this predicate. So for binary operations, we are using the same approach, the same idea, except now we have two operands and not one, so we have to account not for one unique range, but for a unique pair of ranges as an input to an operation. So say if you have vectors A and B, and you want to perform an element-wise sum, you will create 4 different groups where you combine green elements with green elements, orange with orange, and green with orange, and orange with green. And for matrix multiplication, the idea is exactly the same, except you would have to align elements not by their index, but it would be a left-hand side row and the right-hand side column of the matrix. And the expression for actually evaluating the resulting element will be constructed internally by our tool. Naturally, not all of the operations can benefit from simple grouping of elements. So, for instance, if we have a value that is recomputed at every iteration and then propagated, such as an accumulator in faults or an explicit index in the enumerators, then we cannot directly apply this approach. Then, in this case, the analysis falls back to the default behavior and unrolls the loop. However, we noticed that for many of the faults, the structure of this higher order function that is passed to the fault is actually relatively simple. So we can optimize and still make use of this once per range evaluation if we over-approximate the value of the accumulator. And we identified 2 cases when this is possible to do: a general linear expression and a particular case, a special case of the linear expression as sum. So for the sum, it's probably the simplest case because we determined that our domain-specific language has real-valued semantics. The sum in real-valued arithmetic is both commutative and associative, so we can rearrange the elements however we like. And therefore, for each group, we compute the sum with the number, with this simple closed form formula, and then we unroll the error computation using this over-approximated accumulators range. For a general form linear loop, it's slightly more complex because here the resulting value depends on the order of computations. So we first do some pre-processing and we split and sort the groups of elements such that each group only contains consecutive elements and they are sorted starting from the element with the index 0. And then we apply the same approach. We over-approximate the accumulator using this closed form formula, and we unroll the error computations because there is no simple closed form formula for the errors. Now, we implemented all of these necessary components in a tool called DS-tool and evaluated it on the new benchmark set. So since we are the first ones to explicitly target analysis of loops over data structures. There was no standardized benchmark set, so we collected the benchmarks from open source projects in different domains and repurposed some from related work. In our evaluation, we wanted to answer two questions. How does DS-tool compare to state-of-the-art tools, especially in its scalability? And how does an abstraction affect results of our analysis? In order to do that, we determined our benchmarks to have between 10,000 and 700,000 iterations, where each iteration would have between 1 and 1,000 arithmetic operations. We also played around with the granularity of specifications for input data structures and varied them from very coarse ones, where all of the elements inside one data structure would just get one input range assigned, to very fine-grained, where each of the elements would get a unique range and two configurations in between. We compare our tool with two state-of-the-art tools. Fluctuat, in particular, can handle loops without any pre-processing, but only in imperative-style loops. And its baseline analysis is also remarkably effective, so it is more scalable than competitor tools. And among those tools that can only handle straight-line code, Satire was also shown to be the most scalable. And precisely, we will compare two metrics: accuracy in terms of rounding error bounds and performance in terms of analysis time. So when answering the first question, we wanted to know how many benchmarks tools can handle. So we determined that a tool can handle a benchmark if it reports a non-trivial error bound within 30 minutes. And results of our experiments indicate that DS-tool was able to handle many more large benchmarks compared to Fluctuat and Satire. Whenever Fluctuat and Satire did report some values, we also compared their relative performance by normalizing the analysis time of Fluctuat and Satire over DS-tool's analysis time, and noticed that the DS-tool was median 24 times faster than Fluctuat and 260 times faster than Satire, and also it was at least 9 times faster than Satire on large benchmarks. We also compared relative accuracy, and here I should also note that we ran DS-tool with this over-approximated evaluation of faults. So predictably, the accuracy of DS-tool was lower than for other tools, but it is still of the same order of magnitude. So we conclude that DS-tool scales better to large programs because it handles more large benchmarks, computes the results faster without significant accuracy loss. In order to evaluate the effect of the data structure abstraction on our analysis, we compared the DS-tool with an abstraction, but without optimization for faults, to simple unrolled versions of the analysis. And again, we compare relative performance and accuracy. So here, I'm showing you results for the coarsest specification, and for other specifications for inputs of data structures, you can look it up in the paper if you want. So what we noticed is that relative accuracy for all benchmarks was exactly 1. Those are the points that are plotted along the horizontal axis. So it says that our abstraction alone does not have any effect on the accuracy, but it can improve performance, and in the best cases, this is by a factor over 700. So another thing that we wanted to evaluate is how our optimized faults compare to the traditional unrolling scenario. And here again, we are comparing relative performance and relative accuracy. And let me show you a particular example. So this dot stands here for a benchmark that computes an average over 10,000 elements. And this is a specification where all elements have the same range. And using our optimized fault evaluation, we were able to compute results 31 times faster than with just unrolling. and only by a factor of 2.3 less accurate. So you can also navigate these effects by specifying by providing more fine-grained specifications. For instance, for the same benchmarks with the 10,000 elements, but with 1,000 unique range specifications, we can reduce the factor of accuracy loss, but also we are losing some of the performance. So we conclude that our fault optimization provides a viable trade-off between accuracy and performance, and we can also further navigate it by providing different granularity of input specifications. So as a takeaway, I would like you to remember that scalable analysis of loops is still challenging, but we can improve the scalability by using semantic information from functional style specifications. And in particular, we achieve the scaling up by coupling an abstraction of data structures and analyzing only as rarely as possible. Our tool showed that we can handle more benchmarks and do that faster than the competitor tools without a significant accuracy loss. We implemented everything open source, and it is a part of the framework DAISY. So it is available on GitHub and also as an artifact linked in the paper. Thank you for your attention, and I'm happy to take questions.
Okay, questions from the floor. Oh, right at the back.
Let me see. Maybe I missed something, but I think you mentioned when you talk about the fold, you mentioned commutative and associative, but you also mentioned IEEE 754, which.
Right. So there is a difference because the semantics of the DSL itself is real valued.
Okay.
So we are computing sort of against this real valued specification, and then for the order for which we will compute with this real valued specification, if you implement exact that order with floating points, the error bound holds. So our tool actually can generate the code for that. So for the code that is generated by DS2, the bounds will hold.
Okay, that makes sense. That's what I was thinking, but I just wanted to clarify because I was like, that's they don't quite match.
that is true.
Thank
that
you.
is true.
Okay, any more questions? Yeah.
Thank you for your talk. Can you deal with infinite loops?
No. So this approach only works on bounded loops.
Okay.
You need some kind of different way to abstract it. Because if your group is infinite, well, okay, that depends. I think if you have like an infinite data structure, but you apply a map, I mean, that would.
No, but in your benchmark, you talked about filters, and these filters can work forever, and you can infer bounds on these errors.
Right. I guess we use the filters on the bounded data structures, but yeah, if you want to have this kind of infinite filter, then you would need some different, like you need some way to abstract a loop then in a different way.
Okay, any more questions? Oh, yes.
Hello, thank you. About the accumulator, so what you do is you group the elements and you abstract those groups. But I'm not sure to understand how you choose those groups and what are the criteria you use to.
Just a range of values. I mean, this can be so if you specify inside your for each input data structure, you have to specify what is the range, and that's the case where you can regulate it. So if you say you have all of the elements inside your data structure have the same range. I don't know, from 1 to 2.
Okay, but
that's how you know you only have one group. So if you modify it further, say, I don't know, you take a subset of the values and then you multiply it and then concatenate data structures again, then you will get a resulting data structure that will have several groups, right? So it is like each transfer function will affect that. But I think I would have to like walk you through examples. I don't know how general I can answer that question.
Okay, but if you have, so at first you have an array, for example, that has multiple values, and you need to construct those pools of intervals, for example.
That's just provided by the user.
Okay, okay. So this is a fixed amount, fixed number of pools. That's it?
Yes, yes, yes.
Okay,
so
thank you very much.
unless it is modified inside the algorithm, it will be fixed.
Okay, thank you.
The questions keep coming.
No one wants a coffee break.
It's pretty cool work. So I'm curious, how far off do you think this would be from extending it to support unbounded, still finite, but unbounded, like not statically bounded structures?
Can you give an example of such a structure? I'm just struggling to...
I mean, maybe I'm reading more into your examples than you intended, but so for example, you give this example where we know the size of the array is 33. What if we don't know the size of the array? We just know it's finite because it's an array.
Right.
But we might know some information about maybe it has some bound n and the first half and the second half.
Well, I think generally it is a difficult problem for rounding error analysis because, like, if you just take a general case of a loop, the error is unbounded. So you need to know some kind of upper bound on the number of iterations with which you can then compute a precise value. But again, so because we only require you to have a maximum number of, like, maximum size of the data structure, then you can over-approximate.
Okay, any final takers for the final question? If not, let's thank our speaker again.